The aerospace world is buzzing with excitement. The US has secretly tested a hypersonic weapon so advanced that it has stunned military experts and rival nations alike. This breakthrough technology is rumored to be even faster than the classified SR-72 Darkstar, the successor to the legendary SR-71 Blackbird, once the fastest plane on Earth. But what exactly did they test? And how did this cutting-edge hypersonic craft push beyond Mach 6, possibly even reaching Mach 10? Join us as we dive deep into the mind-blowing details of this cutting-edge hypersonic test. Faster than SR-72 that has left experts stunned. Hypersonic aircraft and weapons might sound like something out of a sci-fi blockbuster, but they're the result of more than half a century of research, experimentation, and technological breakthroughs. While many people see hypersonic technology as a game-changer of the 21st century, the truth is that its origins stretch back to the Cold War, when the United States and the Soviet Union were locked in a high-stakes race for air and space dominance. For years, hypersonic technology sat on the back burner, gathering dust in secret military labs due to limited funding and a lack of immediate military applications. But today, with rising global tensions and a renewed arms race, world superpowers are racing to perfect these ultra-fast systems, which can outmaneuver traditional missile defenses and strike targets with unprecedented speed and precision. The journey toward hypersonic flight began in 1959 with the North American X-15 rocket plane, a groundbreaking experimental aircraft that still holds the record for the fastest speed ever recorded by a crewed aircraft, Mach 6.7. The X-15, launched from a B-52 bomber, proved that controlled hypersonic flight was possible, but it relied on a rocket engine, which burned fuel at an unsustainable rate. This limitation made long-distance hypersonic travel nearly impossible at the time. Despite these challenges, the dream of hypersonic flight never faded. Engineers explored scramjet engines, which could theoretically sustain hypersonic speeds without the need for bulky rocket fuel. However, technical hurdles, such as extreme heat generated at Mach 5+ speeds and the need for advanced thermal protection systems, kept the technology from advancing quickly. When trying to build a city bus where 90% of its total weight was just fuel, sounds absurd, but that's exactly the kind of challenge early rocket-powered aircraft faced. Since they had to carry both fuel and an oxidizer to burn it, there was hardly any room left for essential systems like safety features, passenger compartments, or even advanced navigation technology. This made rocket planes not only inefficient, but also wildly impractical for commercial travel. The X-15, for example, one of the most famous rocket planes ever built, could reach speeds of Mach 6.7, but it could only stay in the air for a few minutes before running out of fuel. Now, this is where modern hypersonic air-breathing engines, like ramjets and scramjets, change the game completely. Unlike rockets, which must carry heavy tanks of liquid oxygen, these engines pull in atmospheric oxygen as they fly, making them far more fuel efficient. This efficiency is measured using a key performance factor called specific impulse, which essentially tells us how much thrust an engine produces compared to the amount of fuel it burns. The higher the specific impulse, the more efficient the engine. While rocket engines typically have a specific impulse of around 450 seconds, air-breathing jet engines like ramjets and scramjets can exceed 1,000 seconds, meaning they can fly much farther using much less fuel. That said, not all jet propulsion systems are created equal. Turbojets, the kind of engines found in traditional fighter jets, are great at accelerating from a standstill and can reach speeds up to Mach 2. But beyond that, they become inefficient and struggle to keep up. Ramjets, on the other hand, are designed for much higher speeds, but require an initial push since they can't operate at low speeds. Once moving, though, they can cruise at around Mach 3 to 4. Then there's the real speed demon, the scramjet. This cutting-edge engine can function at Mach 5+, meaning a flight from New York to Tokyo could, in theory, take under 2 hours instead of over 12. Ramjets and scramjets can easily smash past the Mach 5 speed barrier, making them perfect for hypersonic travel. But there's a big catch. They don't work well at low speeds, which makes takeoff and landing a real headache. That's one of the biggest reasons why most hypersonic vehicles today aren't reusable. Take modern hypersonic missiles, for example. They don't just start at hypersonic speeds. First, they use a conventional rocket engine to climb to high altitudes and build up enough velocity. Then they either glide back down at hypersonic speeds or fire up a scramjet engine to keep the momentum going. So the big question is, why not combine a turbojet and a ramjet into one engine? That's exactly what the team at Hermeus thought, and that's how they came up with their game-changing Chimera engine. And they didn't just pick that name randomly. The Chimera, in Greek mythology, was a mythical beast made up of different animals: a lion, a goat, and a serpent. Similarly, the Chimera engine is a hybrid, blending two different propulsion systems into one. This turbine-based combined cycle engine is a total game changer. It seamlessly switches between turbojet mode and ramjet mode. That's what powers their cutting-edge aircraft, the quarter horse, letting it take off like a normal plane and then rocket into hypersonic speeds without breaking a sweat. And of course, hypersonic speeds generate insane amounts of heat. But the engineers at Hermeus have thought of that too, designing the quarter horse to handle extreme temperatures so it doesn't overheat mid-flight. It's a revolutionary step toward reusable hypersonic aircraft, something that was once considered nearly impossible. The Chimera engine created by Hermeus has a standout feature: a pre-cooler. It is like a high-tech air conditioner that cools down the air before it hits the turbojet. This might sound simple, but it's a game changer because it helps Hermeus maximize the engine's performance before it transitions into scramjet mode. This is especially important because we're talking about hypersonic speeds, those over Mach 5. These speeds are the next frontier for military tech, and the Pentagon has been betting big on combined cycle engines that can operate both as turbojets and scramjets to achieve these extreme velocities. Hermeus is a relatively small startup, but they've managed to jump right into the heart of cutting-edge hypersonic tech. While huge corporations or government agencies would typically take decades and massive budgets to create something this advanced, Hermeus did it in just 21 months, with an astonishing budget of only $18 million. That's a fraction of what people expect for a project of this magnitude. For comparison, the United States Air Force's hypersonic technology demonstrator had a budget of over $300 million, and it took years to develop. Hermeus has shown that a little creativity and efficiency can achieve huge leaps in aerospace. When it came time to build their turbine-based combined cycle engine, Hermeus didn't just pick any engine. They went with the General Electric J85 turbojet. This engine has been trusted for decades, powering military aircraft like the Northrop F-5 Freedom Fighter and the T-38 Talon, which are still in use today. The J85 has a legendary track record for reliability and performance in various missions, from tactical fighter jets to training planes. It's an engine with a serious pedigree. Hermeus didn't just stop at the original Chimera engine. After debuting the first version, they were already working on Chimera 2, a more advanced iteration, just 1 year later. And when someone considers that major aerospace companies often take years, sometimes decades, to even dream of launching a new version of an engine, Hermeus's rapid pace of innovation is nothing short of extraordinary. This time, the team decided to go with the mighty Pratt & Whitney F100 engine, the same powerhouse that's been propelling two of America's most famous fighter jets, the McDonnell Douglas F-15 Eagle and the General Dynamics F-16 Fighting Falcon. These engines are real veterans, recently celebrating 50 years of continuous service and more than 30,000 flight hours. They've proven themselves in some of the most demanding situations, from intense combat missions to air patrols across the globe. The new project isn't just about upgrading an old favorite. It's about pushing the limits of what's possible. The Hermeus hypersonic aircraft, a next-level design that's being developed to revolutionize both defense capabilities and national security. The aircraft is no longer a mere step up from existing models. It's a giant leap forward in aerospace engineering. Instead of being a quarter horse, this new design is the dark horse of the sky, built to take on an entirely new set of challenges. Hermeus is designed to fly at speeds greater than Mach 5, 5 times the speed of sound, which is mind-blowing, but it's not just about raw speed. To achieve that kind of velocity, an aircraft must be built to withstand unimaginable temperatures due to air friction at those speeds. This is why the engineering team is working tirelessly to ensure the aircraft's body can handle the extreme conditions of hypersonic flight. And it's not just about speed. Hermes has its eyes set on breaking the record of the legendary Lockheed SR-71 Blackbird, which holds the record for the fastest manned aircraft. Reaching an astounding top speed of Mach 3.3, Hermes isn't just pushing the limits of speed, it's reaching for the edge of the stratosphere. This next-generation aircraft is being designed to soar at jaw-dropping altitudes of 80,000 to 85,000 feet, more than twice as high as commercial airliners, which typically cruise between 35,000 and 40,000 feet. At such extreme heights, the atmosphere is incredibly thin, making conventional flight dynamics far more challenging. Jet engines struggle to get enough oxygen, wings generate less lift, and temperatures swing between blistering heat and bone-chilling cold. To put this into perspective, the legendary SR-71 Blackbird, one of the fastest aircraft ever built, often flew at 85,000 feet to outrun missiles and avoid enemy radar detection. At those altitudes, pilots had to wear full-pressure suits, similar to what astronauts use, because the outside air pressure was so low that their blood could boil without protection. Now Hermes is aiming to go even faster and more efficiently, which means overcoming some of the biggest technical hurdles in aviation history. Hypersonic flight, traveling at over 5 times the speed of sound, creates enormous amounts of friction and heat. The temperatures on the aircraft's surface can exceed 2,000 degrees Fahrenheit, hot enough to melt aluminum and weaken even high-strength titanium. That's why engineers are developing new heat-resistant alloys, ceramic composites, and cooling systems that can withstand these punishing conditions. On top of that, conventional jet engines simply can't handle hypersonic speeds. To solve this, researchers are exploring scramjet technology, which compresses incoming air at incredible speeds without the need for traditional rotating turbines. This could make sustained hypersonic travel not just possible, but efficient. To put it into perspective, traveling at Mach 5 means someone blazing through the sky at over 3,100 miles per hour. At that velocity, the air around the aircraft heats up so much that ordinary materials wouldn't stand a chance. So the engineering team had to rack their brains and dig deep into the science of heat-resistant materials to find the perfect fit for their high-speed machine. They explored some of the toughest materials out there: titanium, nickel alloys, and superalloys, the same kind used in jet engines and spacecraft. These materials are built to withstand insane temperatures, from 1,000 degrees Fahrenheit to over 2,000 degrees Fahrenheit. But when someone starts pushing speeds beyond Mach 6, new challenges pop up. Some experts argue that nickel, while incredibly strong, might be too heavy for an aircraft that needs to be both fast and efficient. That's where carbon ceramic composites come into play. These futuristic materials are not only lightweight, but can also handle extreme heat and stress far better than traditional metals. They're already used in some of the most advanced aerospace projects, including hypersonic missiles and space shuttles. By switching to these next-gen materials, engineers are paving the way for aircraft that can push the boundaries of speed and endurance like never before. These materials have impressive thermal capabilities, with temperature tolerances extending up to 3,100 degrees Fahrenheit for reusable components and 3,600 degrees Fahrenheit for single-use applications. Carbon ceramic composites are widely used in aerospace and automotive industries, especially in components like brake discs, due to their ability to endure extreme temperatures without losing structural integrity. But the team didn't just stop at selecting materials. They also had to think about manufacturing methods. After exploring various options, Hermes made a crucial decision to invest in V3D Sapphire and Sapphire XC industrial 3D printers. These state-of-the-art printers are highly specialized and capable of producing intricate, complex parts with precision and speed. What makes them particularly valuable is their ability to print with Enconos 718, a nickel-chromium alloy known for its excellent heat resistance and corrosion resistance. This alloy is frequently used in high-stress applications like gas turbines and aerospace components because it can withstand temperatures ranging from 423 degrees Fahrenheit to 1,300 degrees Fahrenheit without compromising its strength or durability. In addition to the material's temperature resistance, the use of 3D printing technology allowed the team to create parts with unique geometries that would be impossible to produce with traditional manufacturing techniques. Not only did this approach provide enhanced performance and durability for the Chimera engine, but it also helped the team reduce production costs, making the whole process more efficient and cost-effective. According to Hermes engineers, the quarter horse may look like something straight out of a science fiction movie, but its design and materials are deeply rooted in cutting-edge engineering. While the company did incorporate some advanced modern materials for certain parts of the aircraft, the majority of the airframe is constructed from tried-and-true titanium, a metal known for its incredible strength-to-weight ratio. This makes the aircraft both tough and lightweight, ideal for high-speed performance. The quarter horse's sleek, streamlined look isn't just eye-catching, it's a textbook example of aerodynamic genius. Its design boasts sharp, blade-like edges that smoothly integrate into the aircraft's body, creating a seamless silhouette that's both visually striking and incredibly efficient. This design is reminiscent of the Lockheed SR-71 Blackbird. Just like the Blackbird, the quarter horse is engineered to slice through the air with minimal resistance, making it perfect for high-speed maneuvers. At 40 feet long, the quarter horse is slightly smaller than the Northrop T-38 Talon, which measures 46 feet. But the similarities between the two are hard to ignore. Both are designed for advanced training and light attack roles, offering unmatched agility and performance. The T-38, introduced in the 1960s, is renowned for being one of the most successful training jets ever built, helping to train thousands of military pilots over the decades. Likewise, the quarter horse is intended to serve a similar purpose, but with even more advanced technology, making it a promising contender in the world of military aviation. That said, while the design of the quarter horse is thrilling, it's important to keep in mind that this is still just the prototype. During flight tests, aircraft often undergo modifications based on real-world performance data. Engineers predict that real-world testing will undoubtedly lead to at least some minor design tweaks or adjustments to ensure even better performance, stability, and safety at high speeds and altitudes. Last year was a huge leap forward for the startup, as it made significant progress. The company began testing the quarter horse Mk0, a critical step in integrating the aircraft's main systems and fine-tuning its operational capabilities. The aircraft's ground test stand helped evaluate everything from its avionics to its flight control systems, ensuring each component worked perfectly together. What's even more impressive is that this prototype was assembled in just 6 months, a stunning achievement considering the complexity of the technology involved. During testing, the quarter horse not only met but exceeded all of its planned goals, showing impressive potential. This success caught the attention of the United States Air Force, who have since taken a keen interest in the aircraft's potential for both training and combat scenarios, pushing the boundaries of what we can expect from next-gen military aircraft. In just 37 days, the team at Arnold Engineering Development Complex in Tullahoma, Tennessee, accomplished a series of groundbreaking aerospace tests that are pushing the boundaries of what's possible in aviation. These tests were part of a high-stakes effort to evaluate and refine key aspects of the next generation of aerospace vehicles. One of the main challenges they tackled was human factor evaluations, testing how pilots interact with the vehicle's advanced steering and control systems. They also simulated what happens when the vehicle loses its communication link with the ground, which is crucial for designing robust emergency protocols. They didn't just stop at theoretical testing. The team also assessed radio frequency latency, ensuring that the communication systems could handle delays without compromising safety or performance. Ground handling was another key area they focused on, testing how the vehicle would behave under different conditions when being controlled remotely from the ground. These tests are vital for ensuring that future aircraft can be operated safely and effectively, even when piloted from afar. By early 2024, the Mk0 vehicle completed its tests and made history as the first of 4 planned test vehicles for the quarter horse program. This is a major milestone for the program, which is developing cutting-edge technologies that could revolutionize flight. Then in March of 2024, the team introduced the Mk1 prototype, which was tasked with even more ambitious goals, including remote takeoff and landing, one of the most challenging aspects of autonomous flight. The engineers spent 7 months meticulously assembling the Mk1 prototype, ensuring that every detail was perfect. Once the Mk1 was ready, the team moved quickly, completing all the testing tasks in just 21 days. But this time, the tests weren't conducted at the AEDC in Tennessee. Instead, the team took the Mk1 to Edwards Air Force Base in California, a location known for its history of advanced flight testing. It was there that they pushed the vehicle to its limits, reaching taxi speeds of 50 miles per hour while running the engines at full afterburner, an incredible feat for an unmanned test vehicle. These high-speed taxi tests provided valuable data on how the Mk1 would behave at higher speeds and helped refine its overall stability and control. The team is making impressive strides with 2 more prototypes, Mk2 and Mk3, and the first one is already under construction at the Hermes plant in Atlanta, Georgia. This is a big deal because the Mk2 is set to push the boundaries of flight technology. It's going to feature the Pratt & Whitney F100 engine, which is a major upgrade over the GE J85 engine found in the Mk1. The F100 is known for its incredible reliability and power, making it a key component for achieving the ambitious goals of the Mk2. The primary goal for Mk2 is to break the sound barrier and showcase autonomous supersonic flight at speeds below Mach 2. This is a huge leap in aviation technology, as flying at supersonic speeds autonomously requires advanced systems to handle everything from navigation to emergency responses without human input. This is not just a fast plane, but a machine designed to operate like a self-sufficient pilot in the sky. While exact technical specs for the Mk2 remain under wraps, the engineering challenges being tackled here are revolutionary. As for Mk2, there's even more excitement. While the team hasn't revealed much about Mk2 just yet, it's rumored to be based on the test version of Chimera 2, an aircraft that already shows off some next-level flight features. The roadmap for Hermes suggests that Mk2 will be tasked with something truly extraordinary: a transition from turbojet to ramjet mode in flight. This transition is no small feat, as it involves switching propulsion systems while flying at high speeds and altitudes. If successful, Mk3 will break the all-time airspeed record, which is currently held by the legendary SR-71 Blackbird. The SR-71 has been the gold standard in high-speed flight for decades, so breaking that record is no small ambition. It's something that engineers and aviators have been dreaming about for years. The team isn't just working on aircraft, they're also creating an entirely new approach to test management with the flight deck startup. The flight deck is being developed from scratch to operate in off-grid, standalone environments, particularly in austere conditions where traditional support infrastructure might not exist. It's designed to be fully self-sufficient, allowing for operations in remote areas or during high-risk missions, like those over hostile or uncharted territories. The seats are also specially designed for pilots and payload operators, ensuring comfort and safety even in the most extreme conditions, where every second counts. A small team of 4 highly skilled operational analysts and a few specialized observers are working from within a state-of-the-art high-performance computing center. This isn't just any data hub, it's designed with precision and functionality in mind. Inside, it's equipped with advanced climate control systems that create a perfectly isolated environment to ensure the safety and reliability of critical flight equipment, even in extreme conditions. Despite its cutting-edge technology, the exterior of the center looks deceptively ordinary, like a transport container. This design allows it to be easily transported and set up anywhere in the world, making it incredibly versatile and capable of providing support on a global scale. Why all this effort and innovation? It's all part of a massive push to develop the Hypersonic, a revolutionary hypersonic passenger aircraft that could transform the way we think about air travel. The Hypersonic isn't just another aircraft. It's built to fly at speeds greater than Mach 5, which is more than 5 times the speed of sound. This would allow it to complete over 125 transoceanic routes, cutting travel times drastically. For example, the flight from New York to London, which currently takes around 7 hours, could be reduced to just 90 minutes, making it a reality where long-haul flights could feel more like a quick commute. The engineering behind this aircraft is nothing short of a marvel. The Hypersonic is being developed to become the first viable hypersonic passenger plane, and its first test flight is scheduled for 2029. But before we get there, people will see the testing of the quarter-horse Mk2 and Mk3 prototypes in 2025 and 2026. These prototypes will pave the way for hypersonic flight by testing critical technologies that are key to the Howson's success, such as advanced propulsion systems, aerodynamic designs, and the ability to withstand the intense heat and pressure of hypersonic speeds. One of the most impressive aspects of this project is the rapid pace at which the team at Hermos is moving. Hypersonic flight is incredibly complex, and the engineering challenges are immense. Yet the Hermes team is pushing boundaries, working tirelessly to ensure the technology is both efficient and safe. Their relentless dedication to innovation has raised the expectations for what might seem impossible, and there's little doubt they will overcome every challenge that stands in the way. When people consider how far they have come in aviation, the Howson seems like the logical next step. This technology will not only revolutionize air travel, but it also holds the potential to change the way people think about global connectivity. The ability to travel anywhere in the world in under 2 hours could reshape industries, economies, and even the way people live their lives. The dream of hypersonic flight is on the horizon, and with the progress being made, it's clear we're closer than ever to turning that dream into a reality. Thank you for watching another episode on our channel. While you are still here, click the video on your screen to see more mind-blowing videos like this one.